All right, so this is part 2 of the volumes section 5.2. This one is called volumes with known cross sections. Typically, this is one of the more challenging ones for people to understand, so I'm hoping that some of the visuals that I'm going to give you here are going to help you guys out. So the concept was what we did before was we took some kind of a surface, we took some kind of a two-dimensional area, and we revolved it around an axis and created a three-dimensional solid figure. Well, now the difference is we're going to be given this solid figure. We're not creating it, it's given to us. And what we have to know about it is we have to know something about its base, and we have to know something about what it looks like on top. So you got to know what the bottom looks like, and you got to know what makes up the top part of the solid. So basically what you need to know is if you sliced the solid, what the cross section would look like. That's the hard part to imagine. So what I'm going to try and do is give you guys some visuals to hopefully help that out. All right, volumes with known cross sections. So if you can imagine taking an orange and cutting it in half, and then you place the half cut side down on the table, so basically the open side of the orange. So what it should look like is it should look like a dome sitting on your table. Um, then next, what you can imagine is taking um, paper thin slices in one direction perpendicular to the table. So basically, it's like taking a knife and cutting the orange straight down towards the table. If you can picture all that in your head, which you're doing pretty good if you can, the slices that you're taking are what are called cross sections. Cross sections. Let's make that thinner. And each cross section of the orange is a half of a circle. Now, if you can't visualize this, I'm going to try my best to kind of illustrate that for you. With each one having a different radius, and then the sum of the volumes of all these paper thin cross sections, or semicircles in this case. Let's go with cross sections actually, because they're not always going to be semicircles. That's going to form the volume of the orange. All right, so let me try, and I'm just up here going to kind of try and draw something what that would look like. So um, if you took the orange, cut it in half, it's probably not going to be the best drawing in the world, but you'll hopefully get the idea. So it looks something like that. Okay, and that dotted line represents kind of the back of the orange. So I sliced the orange in half, I sat it down on the table, and then what we're going to do is we're going to take like a knife or something like that, and we're basically going to slice it right here. Probably should use a different color for that. So we're going to take and we're going to slice the orange right there. And what'll be created, and that's not a good slice, is that cross section. Should have gone all the way up to the top. But that's what you're going to get. And then if you slice it over here, it's going to be a much smaller one. If you slice it in the center, it should obviously be the biggest one. But what you can see is that this semicircle is different size than this semicircle. As I start slicing it all the way down this orange right here, the semicircles are going to be different, which means the radius of each one of these semicircles is going to be different. But I know something about the base because I know that the base in this case has an area which is a circle. And then I know that the top of this thing is created when I take slices which are semicircles. Okay, and that's the general concept of what we're trying to do. So you're going to have to know something about the base. You're going to have to know something about this top of it. All right, so this next one, I'm going to kind of skew away from this just a little bit, but I'll still read it. Now imagine another solid with cross-section slices that are squares of different sizes. The sum of the volume of the paper-thin squares is the volume of the solid. In finding the volume of a solid with known cross-sections, the base of the solid is known. You must know how to determine what the base of the solid is. Otherwise, you're not going to be able to figure this out. So let me just kind of give you a general concept here. We're finding volume. So if I were just to draw a very basic rectangle, something like that, rectangular prism of some kind, you know the base of this because you know how to find the area of the base of a rectangular prism. It is a length times width. Well, that would give you the area of the base. And then we would simply multiply it by its height, and then we would get the volume of this thing. The problem is with these known solid figures that we're given, a lot of times this height changes. It's not going to just be a nice little rectangular prism. So it very well could be that you have a rectangular base but now the heights form something like this. That should have gone to the back piece. And what you can see is that if I started slicing this thing one way or the other, it's now going to be semicircles, which are going to create the cross sections, while the base is still just a rectangle. But we have to know what the base is to multiply it by the heights in order so that we can get the volume. So best example that I can give you here, I'm going to get rid of this one for a second here. Oh, that was awful. Try it again. Best example that I can give you is we know that the base of, well, at least for the most part, the base of a loaf of bread is going to look like a rectangle. So if you kind of drew, let's see if I can do this. If I kind of drew the base of a loaf of bread, okay, it's going to look something like that. I'm going to kind of sketch the back of it in here. But then the loaf of bread, hopefully if I draw this right, comes up. And a lot of times it has that little kind of, well, that's not so bad. Something like that. That's what the front looks like. Well, obviously this is not a rectangular slice. It's some kind of really weird looking figure here, and that's not a geometric figure that we would know, but that's what it would look like. And then of course the bread would go all the way back here. Something like this. I don't expect you guys necessarily to draw this. And then it would go out like that, and then back down, and then you get some kind of a little crease in there or something. But anyway, you can start to see that if you looked at one single slice of the rectangle of this piece of bread, one single slice is going to look like this. So if I can take and add up all those thin slices all the way from here to here, I'm going to get the volume of that loaf of bread. So we would have to know that the base is a rectangle in this case, and then we'd have to know how to find this area, however that is, and then add up all the areas from here to here. That's what we'd have to know. Not quite as easy to do with something like this, but everything that we're going to be given is geometric shapes of some kind. All right, so that's enough of the illustrations there. Hopefully that did something for you. So let me show you something which looks a little bit different, and I hope that this video works better than the last one did. All right, so what this is it gives us a circular base, and it tells us that the cross sections of this base are going to be, looks like equilateral triangles of some kind. So what you should be able to see is depending on where the equilateral triangle is, makes difference as to how big the equilateral triangle is. The further we go one direction, the smaller the triangle is. The more towards the center we go, the bigger it is. And then obviously the further we come towards the other side, the smaller the triangle becomes. And you can kind of see what the figure looks like. Kind of looks like a gumdrop or something, I don't know. But you can see how a circular base could have a different cross section and create some kind of a three-dimensional figure. So it doesn't just have to be an orange. It could be made by a whole bunch of different things. So again, hopefully that's a pretty good representation. What does this do? Oh, it just gets rid of the solid. So what it is you're taking all those triangles from one point to another, and you're going to create this solid. So there you go on that one. That worked out a little better than I thought it would. That's good. All right, let's get to some examples. All right, so finding the volume involves the same two-step process that we had before. you need to know, find an expression for the area of the geometric shape of the cross section. So they either have to give you the area, like tell you that it's a rectangle or a triangle or a semicircle or something like that, that you can actually take, and then you'll have to know the formulas for those. And then you're going to take the integral, which simply means to add all of those areas from one point to another of that expression. So we're going to add a whole bunch of areas of geometric figures over some kind of a base. So therefore, the volume of the solid with known cross sections is given by, the volume is going to be the area times dx or dy, depending on if we do this cross sections perpendicular to x or perpendicular to y. Note that if the cross sections are perpendicular to the x-axis, the integral is going to be with respect to x. And if the cross sections are perpendicular to the y-axis, the integral would be with respect to y. So this would be dx's and this would be dy's. All right, example. Let's see. A solid has a base that is a circle with an equation x squared plus y squared equals 1. So this is definitely something you're going to have to start to recognize. This is your standard circle centered at the origin with a radius of 1. X squared plus y squared equals r squared is your standard circle centered at the origin. If there was a number out in front of either one of these that was two different numbers, like one was a 4, one was a 9, that is no longer a circle, it's an ellipse, and we'll deal with elliptical ones as well. And we'll sketch these so that you guys can get reminders. Cross sections perpendicular to the x-axis are semicircles. So this is really going to look very much like our sliced orange here. It says the semicircles with their diameters in the plane of the base. Verbiage, that's terminology that you guys are going to have to understand. It just means that the diameter runs the whole way across the base. So first let's sketch the base of the solid itself. Well, the base, again, is this thing right here. It tells us that the base is going to be a circle with this equation. So if that's the case, it's centered at the origin, radius of 1. Okay, looks something like that. Radius of 1. This is the base. Okay, that's what it's going to look like. And then we're going to take, and that's basically, if I'm looking straight down at the table, this is what it would look like. If I looked at the side of the table, it would, look like half of an orange. So this is what the base is. And it says that cross sections are going to be perpendicular to the x-axis. Well, this is the x-axis, so perpendicular is this way. So if I take cross sections, I'm going to cross section this thing from here to here. Okay, and it says the diameter is in the plane of the base. So this is the diameter right here of my semicircle. Now the hard part is to imagine that the semicircle part comes up off of your page and does something like that. It's hard to see that visually three-dimensionally, but that's what it does. So it comes up off of the page and creates a semicircle. So we're basically taking the knife and we're slicing it straight down this way as if the knife is going towards the table. Remember, this whole thing is like is your table. This is the flat table right here. So find the sketch of the base of the solid and its solid itself. So this is our diameter, the green line. And the diameter is going to change. It's smaller here than it would be right here, and way over here it's going to be really small. Hopefully that makes some kind of sense. And so that's -1 and that's +1 right there. I'm sorry, that's -1 still. Okay, determine the radius of the semicircle. Okay, so this is where it gets tricky because now we have to do some algebra. In order for us to determine the radius of the semicircle, we're going to have to start with this equation. So the radius of the semicircle goes from here up to here. Well, that's just basically the top part of this equation. This is not a function, fails the vertical line test, because if you drew a straight line through here, it would not be a function. But we can still kind of solve it like a function, because I can still solve this for y or x. And because we are crossing this thing, cross-sectioning this thing perpendicular to the x-axis, I'm going to have to solve this for y, so it'll be y equals something with x, so we can do this as a dx. So I'm going to solve this equation right here for y. So x squared plus y squared equals 1. Solving that for y, we're going to get y squared equals 1 minus x squared, and that makes y equal to the positive and negative of the square root of 1 minus x squared. So just the positive part of that is the top half of the semicircle. The negative of that square root is the bottom half of that semicircle. So the whole thing creates the entire circle. So we have explicitly solved for y by including the plus and the minus. The radius, however, is just the top half, because I only need to go from one way, or technically I could go to the bottom half, but it's not both. It's not the plus and the minus, it's just one of them. So the radius goes from here up to the top half of the circle, which is just the positive of this. So I can say that the radius is the positive square root of 1 minus x squared. Now, keep in mind, my cross sections are semicircles, so I need to know the area of a semicircle. Well, the area of a semicircle is, well, the area of a whole circle is pi r squared, so the area of a semicircle is 1/2 pi r squared. I'm going to add up all of those from here all the way over to here, all the semicircles that I can create. Okay, so let's go ahead and do the math here. So I'm going to integrate from -1 to 1, because if you look at the circle, it goes from -1 to 1. So yes, you do need to be able to figure that out. Of all the 1/2 pi r squareds, but r is this, and it's dx. All right, so I can go ahead and take the 1/2 pi to the front. This is my volume, by the way. And I'm going to integrate from -1 to 1. If I square this, it just gives me 1 minus x squared. And then I can go ahead and take antiderivatives. So 1/2 pi x minus 1/3 x cubed from -1 to 1. And let's see what we're going to get. So 1/2 pi is consistent through the whole thing. So I'm just going to go ahead and plug 1 in. That's going to be 1 minus 1/3 minus, now if I plug -1 in, that's going to be -1. Cubing -1 is negative, so that's plus 1/3. All right, let's combine the common parts. So 1 minus minus 1 is 2. -1/3 minus 1/3 is -2/3. 2 in terms of thirds is 6/3, so this is going to give me 4/3. So 1/2 pi times 4/3. Let's see, the 2 is going to become a 1, that's going to become a 2. So really what I get is 2 pi thirds. All right, so let's see. Does that answer actually make sense to this problem? Well, we can actually figure this out pretty quickly, because really what I was doing was I was taking the volume of a half of a circle. Well, volume of a circle is 4/3 pi r cubed. Probably would have been a lot easier to do this because I know the radius here is 1 of the circle, which is just going to give us 4 pi thirds. So that works. You won't always be able to check it that way. Oops. That is the volume of a circle, of a whole sphere, excuse me, but we have to do half of that. Half of that is going to be 2 pi thirds. So that works. Sorry. There we go. Again, you won't always be able to check it that way, but in this case, we can. All right, so there's the first one. Let's see how we doing. We're at 19 minutes. All right. I think we're going to go ahead and stop the video here at about 20 minutes. We'll come back with a second video. Should definitely be under 20 minutes because I did all the preliminary stuff on the first one.